Okay, we can do it now. I'm just going to edit all this out. Okay, today we're going to talk about unit conversions as we talked about already. This is our third take. All we need now is one of those things and we're ready to go. So take 4. We're going to review unit conversions and then we'll move into derived units today. So this sheet here, this screen here, we've been doing basic conversions for 2 days now? And we've stuck with some of the base unit, meter, liter, things like that. But I just wanted to show you this screen because later on today we're going to move into derived units. And so I want you to understand what they mean. And so I figured it was important for me to tell you that when we take our measurements of whatever quantity we're talking about, there are only 7 units that are what we would call base units, meaning a direct measurement of one of one thing. What's going on here? Only one measurement. Only 7 units that are base measurements. Every other thing we report, every other quantity, is a combination of those base units. So these are the base units themselves. For the quantity length, we have the meter. For mass, kilogram. You can read them for yourselves. You will never in this class see the ampere. That's the units of electric current. You will definitely never see the candela, guaranteed. So just keep in mind that those are what we call base units and everything else is derived from them. These are found in your textbook, so I'm not going to kind of dwell on them for too long. Does anybody have any questions on that? All right, I'm going to go ahead and go forward. If you didn't write them all down, it's totally fine. It's just kind of introducing you to the future. So this is what we've been doing thus far. When we have metric equalities. We have metric equalities. This is the same little system that we used the other day. Remember, any 2 on that are equal. So if you have this written down already, there is no need for you to write it again. Just wanted to make sure you remember it. And they can be used with any of those base units you saw on the previous page. So something as silly as a nanocandela. Yes, that is a real thing, I suppose. I've never seen it used, but you can report nanocandelas or micromoles. And one of my chemistry professors used to say millimole. It was the funniest. I just thought it was funny because he had kind of this weird accent. And moles is the unit of amount. And when you're working with very small volumes of solution, this was an advanced kind of it was physical chemistry in college. It was pretty high level stuff. But anyway, he would say millimole. It was so funny. And it doesn't matter. It's a side note. So just as an example to make sure you remember how this system works, I'll just make up something stupid. So when we convert between 2 units, what we need to do, first of all, obviously, is read it. Identify the given and the unknown, just to make sure we have this for posterity. The given is the value that has unit and number. The unknown is the one without the unit, obviously. It's not always going to be in this format, remember. Sometimes the question will say something like, how many kilograms in 100.2 centigrams? Just make sure you can translate. I'm sure you can. Once you identify the given and the unknown, you ask yourself, do I have an equality that will allow me to convert between centigrams and kilograms? And in this case, you should recognize that centigrams and kilograms are nothing more than metric prefixes. And so, yeah, we have a relationship. It's in this mess up at the top here. We find the 2 units involved, the centi version and the kilo version, and those become our equalities. The equality we're going to use in this case, just pulling it out so you can see it, we don't use the U, we use the gram in this case. Remember, the U is a generic placeholder. And now to solve the question, we start by writing the given, 100.2 centigrams, and we multiply the given by a conversion factor. A conversion factor is a fraction written from an equality. And I want to make a special point here for you guys here in class today. I've had at least 3 students come and ask me for help, which I do encourage. But every single one of those students had an equal sign written right there. That's not There's no equal sign there. We are multiplying by a conversion factor. The equal sign here, yeah, we're trying to find the equivalent amount up here, but here we are converting. That involves multiplication. It didn't actually affect their answer, but technically, if you're using algebra correctly, the math is a little different. So make sure you understand that it's not an equal sign, it's multiplication. Okay, now our guiding principle here is letting the units guide us. So in this spot here, we have to decide, which of these two values goes in the denominator. Which of those two goes in the denominator? Now, how do we know it is 100 centigrams, as Shayla said? Class, how do we know? The units cancel. It's okay to speak on video. You might be discovered by an agent that way. I might get an email. Oh, who is that person I heard speaking? I'll say, oh, it's me, of course, and I'll take all the credit, but that's okay. So we have centigrams on bottom, so that cancels. Now, what number goes here? How do you know it's 100? Did you just decide? Did you just say, oh, look at all these numbers. I feel like 100 today. Did you? No. You copy the numbers from the equality. That's another point that a lot of students screw up. We copy the numbers from the equality. And so, making sure our units cancel, we're going to get 0.001002. Excuse me, I should have put that next to the... There. Here's our answer. Do we agree? That's basic conversions. Okay, so let's move forward now, and let's talk about derived units. We're going to use the same technique. Please don't lose that technique. Canceling units, multiplying givens by conversion factors. That never changes. Now, derived units, the SI, by the way, stands for the, I can't say it, it's French, Système International. It's a metric system. Okay, SI, it's a metric system. The derived SI unit, units are combinations of those base units. Every example you see here is a combination of two or more of those base units on the previous slide. Examples, for volume, it's length cubed. So some examples are meters cubed, centimeters cubed. Now, if you remember, one of the units of volume that we see often is liters, or milliliters is a version of. That's actually not a metric unit. It's a unit that is derived from metric units. It is basically length cubed. So at this point, I think I'll just give you the equality that you're going to use often. Here is an equality that you should write down. And it goes to show you that the liter, which was not a base unit, is in fact a derived unit. It is related to length cubed, the combination. So you guys, do you understand what I'm saying by combination of units? That cubed there means that volume is, if we're reporting volume in units of meters cubed, that it is meters times meters times meters. There's more than one unit there. In that case, 3 of the same, but still more than one. Does that make sense? Area, length, excuse me, that should be length. Squared. Some examples, meter squared, and so on. Anytime you see length cubed, volume. Anytime you see length squared, area. Don't forget that. Anytime. Okay? Density. Mass divided by volume. So, as an example of units you might see, grams per milliliter. We read that as grams per milliliter. Do you see the mass and the volume in there? It's mass divided by volume. It's a combination of units. Now, this one I want you to pay careful attention to because we're going to use this in some examples today. Look at the way this is set up. Does that remind you of something? Have you seen these fraction bars with units on top and bottom? What does that look like? What does it look like? What have we been using where have we been using things that look like this? What have we called them? Conversion factors. Ding, 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 ding. Alert, it's coming. Just because they're derived units doesn't mean you can't use them as conversion factors. The guiding principle will be you use them so that the units cancel. That doesn't change. And so things that look like this can be conversion factors as long as the units cancel. Just watch for it. I'll go quickly through these. Force equals mass times acceleration. You don't need to know these. I'm honestly not even going to do pressure because it's not worth our time. But the units of this would be kilogram times meters divided by seconds squared, as an example. Those are just examples. We're not going to use this one in conversion, so don't panic. Any questions on derived units, where they come from? Let's just practice using them. Okay. So let's use it. Let's do a simple example. We're going to use density. So let's say we have this particular substance. We'll call it wagolonium. It's a very rare element that's only found in this classroom. Okay? And so the density of wagolonium turns out is 2.6 grams per, let's say, cubic centimeter. Do you guys remember what the definition of density was from the previous page? Mass divided by volume. Look at the units there. Mass divided by volume. Is that the only way I could report density? No. I could report it in any unit of mass divided by any unit of volume. It is still density. Density is defined as mass divided by volume. Doesn't matter what units it's reported in, and you must recognize it as such. Now, here, a point I think I need to make. What this means mathematically, because some students will screw up on this. If I was to write this out in its most expanded form, this is what it would mean. That's the conversion factor. It doesn't have a 1 there. You have to understand that the number in front is attached to the numerator unit per 1 on the bottom. Like if we're traveling 60 miles per hour, 60 miles divided by 1 hour is what that means. Agreed? You all have to understand that. So remember how conversion factors work when they're written in this form. I could use it like this. What is the other form I could use this? What's the other form? Come on, guys, wake up. What's the other form I could use this as a conversion factor? The reciprocal. What determines which of the two I will use? I'll pause. Uncomfortable silence. What determines which of these two that I'm going to use in my calculation? The unit in front of it. What do I want to cancel? If, for example, I wanted to convert from grams to cubic centimeters of wagolonium, if I wanted to do that, if this was my given and this was my unknown, which of these two forms would I use as the conversion factor? I would use this one. If I wanted to go cubic centimeters to grams, of course, I would use the other one. 2.6 G over 1 cm cubed. Agreed? Does anybody have any questions on that? Okay, well, let's do one together. Oops, that's not a very good color choice. So here's our example. How many grams of, well, I'll just put a W for wagolonium, in 2.97 cubic centimeters? And I am going to need you guys to use your calculators for me here. Okay. Look at the question. The first question first thing we do is we read it. What is the given? This one. The unknown. So the units of the given are centimeters cubed, volume. The units of the unknown, grams. Agreed? Class, do you have an equality that relates volume in cubic centimeters to to mass in grams of the substance wagolonium? Do you have a relationship between the two? I'll give you a hint. Yes! What is it? Density! That's what that is. That is a conversion factor. Any derived unit in existence can be used as a conversion factor. However, it's limited. For example, this density here can only be used as a conversion factor between grams of wagolonium and centimeters cubed of wagolonium. How are you supposed to know that? How are you supposed to know that this conversion factor can only be used between those two units? Can you speak a little louder for me? Yeah! That's what those are telling you. That conversion factor is saying, I can only be used for these two things, nothing else. Do you understand? Are you sure? Okay, well, let's do it. Let's find out. So let's do it. I'm running out of room, so I'll put the answer up here. So once I've realized I have a relationship, an equality, what do I write first? The given. Oops. 2.97 centimeters cubed. I'll leave the W off to save time. Once I write the given, do I put an equal sign or a multiplication sign? Multiplication, fraction bar. Okay, what conversion factor am I going to use in this location? Density! That is the conversion between volume and mass. What unit will go on bottom here? Centimeters cubed. What unit will go on top? Grams. What number do I write where my marker is moving? Look at this. What goes by the centimeter cubed? 1. What goes here? That's it. Look at the units. They guided us. Can somebody tell me what the result of that calculation is, please? 1.722? 7.72. So I'll just round to 2 sig figs. We haven't talked about that, but that's okay. There are 7.7 grams of wagolonium in 2.97 cubic centimeters. That makes sense. Every cubic centimeter had 2.6 grams, so nearly 3 of them should have it nearly 3 times 2.6 grams. Does everyone understand how that works? Nice and simple. Let's try a couple more. Density is the one we're going to work with. So I'll make up another number. It doesn't matter the name of this stuff. I'm gonna give you the density of this stuff. We'll just make that 3.2. It's tough to see that decimal point. So let's do like 2 or 3 examples. Here we go. We'll do them quickly. So for the first one, how many milliliters of this substance in 6.8 grams of the substance? Okay, I'm going to go through it just to bore you. Do we have a relationship between the given grams and the unknown milliliters for this substance? Yes. This is mass and volume. Therefore, your brain should immediately be looking for density. Mass and volume. Density. Do we have the density of this substance? Yeah, we do. And it happens to be in the units that we need, grams and milliliters. Perfect. So once we recognize we have a relationship, an equality, then we write the given. We multiply by a conversion factor written as a fraction. What unit goes on bottom in my conversion factor? What unit goes on top in my conversion factor? And so the numbers are 3.2 and 1. At this point, I'm going to pause because I'm starting to go fast. If you don't understand why I'm writing these in this form, you need to ask me now. It will be edited out of the video. Yeah, do you have a question? Yeah, I gave you the density of this substance, so all the examples on this screen will be using that density. Is it that answer your question? Okay. Anybody else? Okay. Does someone have a result for me? I don't have a calculator. Go ahead. I'm sorry. I'll have to. Thank you. I have to honor the hand raise. Okay. We good? Okay. Part B. That's not a good example. Let's see, 6.8 milliliters equals how many grams? Okay, here we go. We do have a relationship. I'll cut it out, all the speech. Milliliters on bottom, grams on top. What number goes here by the milliliters? Read it carefully. What number goes where I'm writing right here? 1. First of all, how did I know to put milliliters on bottom? To cancel. How do I know there's a 1? I looked at the given relationship. It is understood to be per 1 milliliter here, so I copied the 1. And on top I put the 3.2. And in this case, can somebody give me the result? 2 sig figs? 21.7. I'll just round it to that. It's the 10th place. Are we good? Last one. Okay, don't freak out. You can do it. Whoa, hold the phone. Waggle's a jerk. You didn't teach us how to do this, Waggle. Oh, yeah, I did. You just got to think. You got to be calm and think. You read the question. You're being asked to determine kilograms. Kilograms is a unit of what quantity? Mass. You are being asked to find kilograms from 6.8 cubic centimeters. Cubic centimeters is what quantity? Volume. Do you have a relationship between the mass and the volume for this substance? You do. It's 3.2 grams per mil. That can't be used with those two units, can it? Can it? But what if we could somehow convert centimeters cubed into milliliters? Then I could use this to cross over into grams. And then once I had grams, could you convert grams to kilograms? Do you see the path? It doesn't have to be one fraction bar. You can cross multiple as long as the units connect you. That's your guiding principle. So you just have to be able to look ahead. You could, honestly, to be honest with you, we could use, if I go back to, this, I could have been a jerk. And in years past, I have been a jerk. I could have asked you to convert from, I could have given you a number in nano something and said, how many giga of that are there? And I could have made you do one step at a time. It would have worked. You understand why? I mean, you'd basically, like from point A to B, and then from B to C, and then C to D, you'd end up canceling all those steps in between. And so there was no point to it. Right? You understand? So, but sometimes it's necessary to do multiple, sometimes it's necessary to do multiple steps. So we're going to do that right now. So here we go. I start by writing the given. What am I going to convert centimeters cubed into? That's a bad question. Knowing that I have to cross over from volume to mass at some point, and that this is the density. What unit should you be trying to convert centimeters cubed into so that you can use density as a bridge? Everyone needs to understand the answer to this question. The answer is milliliters. Because only if we have the unit of milliliters can I use this as a bridge, as a conversion factor. Do you agree? Do we have an equality between centimeters cubed and milliliters? You do if you took notes today. Do you remember from a previous slide what it was? It is equal. Those two are equal. 1 to 1. Don't forget that one. It's very useful for us. Okay, so I'm going to use that equality. What unit goes on bottom? Centimeters cubed. What goes on top? Milliliters. This conversion factor is that equality. It's designed to take me from centimeters cubed to milliliters so that I can then use density to cross over to grams. Can you see it coming? Anybody not see it coming? Okay. What number do I write here? What number do I write here? If I stopped now, what will I have calculated? Milliliters. Do you see it? Is that what I want as my answer? We have to continue. I want kilograms. Class, do we have a relationship between milliliters of this substance and kilograms? Do you have an equality between milliliters and kilograms? You don't. You do have milliliters to grams. So, let's convert from milliliters to grams. Why did I do that? I'm sorry, that's a bad question. I did that in anticipation of the next step. What is the next step going to be? If I stop now, I'd have grams. But I want kilograms. So what do you think the next step here is? Grams to... You see it. We could do this all day. We could make a string of 5,000 of these. As long as they were all equalities and the units matched, it wouldn't matter. We get the same answer. We could go in circles. I could keep converting back to something all day long. and it'll work. Let's copy the numbers. What number goes here where my little cursor is wiggling? What number goes here where my cursor is moving? How did you guys know? Where did we look for those numbers? That's density right there. Look at the units. They'll tell you mass and volume. This is that equality over there. This is a metric conversion. What number goes here from your number line system? What number goes here? 1. What number goes here? Yes, you can use 1 kilogram per 1,000 grams if you wish. If you remember that from middle school, that's fine. Okay. Can somebody tell me their answer? Since I don't have a calculator, I need you guys to help me. I recommend all of you who have one out do it so you can verify and we all agree. For those of you who aren't sure how to do this, all the numbers across the top are multiplied. I always recommend, I'm not going to require it, but I recommend that when you enter two numbers, you push equals and then go again. I recommend you multiply the top, so 6.8 times 3.2 equals, times 0.001 equals. And that'll be your answer, because then the bottoms are all 1, so it doesn't matter. Does someone have an answer?
I got 0.021.
7? Do we agree? Okay. This is something we need to overcome. You're simply using you're not even doing math. You're using a calculator and you're afraid of saying, really? You're just pressing numbers on a machine. This is not hard. You have to have confidence in using a calculator. You have to, because it'll never go away. You can't put your head in the sand and think, oh, next week we won't have to use calculators. No, no. You have to become proficient. So that right? Do we agree? Does anybody else get that number? Fantastic. I'll assume that's correct. Does anybody have any questions on, obviously that was fast. Now it's on you to practice. We'll do some practice together. No questions? Okay, so you had some homework from a while back. I want you to add those three problems, 17, 18, and 19, and turn it in before you go today. The answers are in the book. The solutions manual will be out. I will be out to help you, okay? Or I'll be here to help you. Okay, good luck.